After studying this module, you shall be able to know further about representations, generate representation using general vector as the basis of representation, generate representation using rotational vectors as the basis, generate representation using position vector as the basis, know the effect of symmetry operations of C2V point group on general point group, verify some of the products of the matrices corresponding to symmetry operations. We have seen that unit vectors lying along Cartesian coordinate transform only as plus minus 1. The unit vectors lying along mutually perpendicular axes hence do not contribute to other coordinate under the effect of symmetry operation. The operation we consider were such that these could transform unit vectors only in plus minus 1 forms only. Now let us take a general vector as the basis for representation. Now we will take general case of representation in which vectors of any length, say Lx, Ly, Lz, can be along xyz axis, but angle of rotation is theta is equal to 2 pi by n. Axis of rotation is taken along z axis. So, vector Lz will lie along z axis and will not change by the rotation about z axis. This type of rotation is shown in the by an angle of theta. Z axis is not shown for the sake of simplicity, and so Lx, Lz along z axis is not shown. So, problem is reduced now only two-dimensional, that is only in xy plane. By Cn rotation, Lx will not change, Lz will not change as it lies along z axis. We can write the Cn effect on Lx and Ly as shown into this, that is Cn operated on Lx, Ly goes to Lx dash, Ly dash, or Lx, Lx dash, Ly dash are given in trigonometric forms as this. And also this slide represents the equations which correlate Lx dash with Lx, and in matrix form the effect of operation of Cn by an angle theta, we get a matrix corresponding to this Cn axis which has been rotated by theta angle as cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1 as the matrix corresponding to Cn rotation which operates on vectors Lx, Ly and z along the xy axis, and here the angle of rotation can be any as shown over here. Let us take a general point xy and perform similar Cn rotation by an angle theta, and the new point is x2, y2. The result of this are shown into the, here I am giving a clockwise rotation to this vector or point x1, y1 which is lying into this. Now we write down the coordinates of x2 and y2 in terms of x1 and y1 and see what is the relation between them. x1 is equal to r cos alpha, y1 is equal to r sin alpha, x2 is equal to r cos of theta minus alpha, that is r cos theta cos alpha plus r sin theta sin alpha, or is equal to x1 cos theta plus y1 sin theta, and y2 is equal to minus r cos of theta minus alpha is equal to minus r sin theta cos alpha plus sin alpha cos theta Here minus sign comes from x, y goes to minus y, or y2 is equal to minus x sin theta plus y cos theta, or z2 is equal to z1 as we are carrying out rotation about z-axis. Therefore, the equation relating x1, y1, z1 and x2, y2, z2 can be written down as like this. x2 is equal to x1 cos theta plus y sin theta 0 z1, y2 minus x1 sin theta plus y1 cos theta plus 0 z1, z2 is equal to 0 x1 0 y1 plus 1 z1, or we say x2 y2 z2 new coordinates are equal to matrix corresponding to Cn rotation, that is cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. Matrix for Sn can be easily worked out if we take matrix for Cn axis and matrix for sigma xy. Sn we know it can be defined as Cn followed by sigma xy. Let us operate Sn axis on a general point x1, y1, z1. Sn axis lies along z-axis and perpendicular to xy plane. This effect can be represented as Sn operated on x1, y1, z1 is equal to Cn followed by xy operated on x1, y1, z1 to get x2, y2, z2. Now we write down matrices corresponding to Cn axis and sigma xy. Cn is given cos theta sin theta 0 minus sin theta cos theta 0 0 0 1, and matrix corresponding to sigma xy as 1 0 0 0 1 0 0 0 minus 1. Therefore, Sn is equal to Cn followed by sigma xy on the point x1, y1, z1. Now take the matrix corresponding to Cn and corresponding to sigma y, multiply them together, you will get the matrix corresponding to Sn, that is cos theta sin theta 0 minus sin theta cos theta 0 0 0 minus 1. This is the matrix corresponding to improper axis of rotation, that is Sn axis. In case of Sn axis, z1 also changes sign. This due to reflection of z in xy plane. z1 goes to minus z1, or z1 is equal to minus z. All the matrices that just have been worked out using vectors along orthogonal Cartesian coordinates only. Now we come across about rotational vector in our dealing with quantum chemistry. Rotational vector as the basis. In addition to linear vector, there is a need for rotational vector which have been defined, written as Rx, Ry, Rz. These are the clockwise direction or clockwise rotation about xyz axis respectively. Gaseous molecules are always tumbling, and these tumblings can be resolved in rotations about x and yz axis and needed in rotational spectroscopy. The symmetry of these rotations is very important in spectroscopic applications. These rotational vectors are shown given. Let us see the effect of symmetry operation E C2 sigma xz sigma yz of C2V point group on this rotational vector. If a rotational vector symbolized by a curved arrow changes direction on performing symmetry operation, it will be antisymmetric with respect to that symmetry operation, that is -1 effect. If direction of arrow is not changed, it will be symmetric with respect to +1 effect, and these effects are shown in the diagram. Let me just explain one of these. Now if I take, this is say the mirror plane, I am taking this as sigma xz. If my arrow strikes over here, in mirror it will look that arrow is coming out of this. In mirror the arrow will look like this. Here mirror arrow strikes like this, and in mirror it will look like this. It means the direction of the arrow is changed. Similarly, if I have this my yz plane, if the arrow strikes like this, in mirror it will look that it is coming out. So whenever the arrow strikes the mirror, its direction is reversed. Now whenever the arrow strikes a mirror, its direction will be reversed. So the effect of these various symmetry operations of C2 viewpoint group on Rx, Ry, Rz are summarized into the which are shown over here. That is, the first column gives Rx, Ry, Rz, and E operation leaves them unchanged. That is Rx, Ry, Rz. C2 about Z axis, Rx goes to minus Rx, Ry goes to minus Ry, and Rz remains same. Now sigma xz minus Rx is obtained, Ry is same, and minus Rz. Sigma yz, Rx minus Ry minus Rz. Now this table summarizes the effect of this. Now let us take important point, position vector as the basis for representation. Molecular properties which are not always located along x, y, z axis can be expressed by position vectors. Commonly these position vectors lie in a general direction. Such vectors can be resolved into three components along x-axis, y-axis, and z direction. Now let us find how the transformation properties of these position vectors relate to representation of that point group. Consider the vector r, whose base lies at the origin 0, 0, 0, point of Cartesian coordinate system, and whose arrowhead is at the general point A, that is x1, y1, z1, and this is shown into the, since the base of the vector is at the origin and not shifted or not changed by any of the symmetry operation, so only the head of the arrow will be considered. We will concentrate on the coordinates only x1, y1, z1 of the arrow before and after performing symmetry operation on this position vector. Let us take the effect of symmetry operation again, that of water molecule E, C2, sigma xz, sigma yz, and find the matrix representation for these symmetry operations using coordinates of the position vector A as the basis for representation. We will find the matrix corresponding to this symmetry. Let us see the effect of E operation. This E operation on general point x1, y1, z1 can be represented as E operated on x1, y1, z1 gives me x1, y1, z1 because it does not change. So x1, y1, z1 that remains same, or in equation form I can write down E operated on x1 gives me x1, and equation is plus 1 x 0 y1 0 z1. Similarly, E operated on y1 gives me equation 0x1 plus y1 plus 0z1. E operated on z1 gives me 0x1, 0y1 and plus z1, where x1, y1, z1 are the component of vector r along x, y, z axis. These components are not shifted by symmetry operation A. In metric form, these equations can be written down as shown over here, and the ultimate matrix for E is 1 0 0 0 1 0 0 0 1. What is the effect of operation C2? C2 lies along z axis. It will not change the z1 coordinate. It will only change x and y will be affected. Since rotation C2 is, that is 180 degree rotation, x1 and y1 will only change their direction and will be minus x minus y. The effect is shown below like this, and in matrix form, vector goes from quadrant 2nd to quadrant 4, x2 is equal to minus x1, y2 is equal to minus y1. x1 is already negative in quadrant 2nd and it becomes positive in quadrant 4. Thus its sign is reversed or direction is reversed. Net effect is minus 1 effect for x1 and so on. The three equations for C2 operation on x1, y1, z1 are written as x2 minus x1 is equal to, equations are minus 1x 0y, y1 0 z1. For y2 the equations are 0x1 minus y1 0 z1, and for z equations are 0x1 0 y1 0 z1. In matrix form these equations can be written down as shown. C2 operated on x1, y1, z1, and we get the matrix corresponding to C2 operation as minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Now effect of sigma xz operation. It will transform x1 into x1 and y1 into minus 1 coordinates, and z1 goes into z1. So x is negative in second quadrant and it will remain same after reflection in xz plane, and these effects are shown in the below, and the equation corresponding to these operations are for x2 plus x1 0 y1 0 z1, for y2 0x1 minus y1 plus 0 z1, for z 0x1 0 y1 plus z1, and in matrix form these equations can be written as shown into the. So therefore the matrix for sigma xz operation is 1 0 0 0 minus 1 0 0 0 1. Similarly, we can write down the matrix for sigma yz, and this is minus 1 0 0 0 1 0 0 0 1. So the matrix corresponding to these symmetry operations of C2V point group have been generated, and table a 3:3 matrix for each of the symmetry operation of C2V point group, for E, for C2, for sigma xz and sigma yz. And these four matrices, each corresponding to E, C2, sigma xz and sigma yz, is written as star matrix. That is, we are having a representation in terms of matrices. Now question arises, the matrix representation which we have obtained, is it true representation or not? So let us check whether these are true representation for each and every symmetry operation. We have to take the product of symmetry operation and product of corresponding matrices and see whether these are correct or not. Group multiplication table for C2V point group is shown in this, where we have given various symmetry products. The various symmetry products of the symmetry operation of the water molecules are shown in this table. Let us examine some of the symmetry operations product and check the corresponding matrices. Let us take C2 operation into C2. To check the correctness of these matrices which have been developed for various symmetry operations, let us carry out certain products. C2 into C2. According to that table it is E. So I take the matrix corresponding to C2, multiply by the matrix corresponding to C2, I get a matrix 1 0 0 0 1 0 0 0 1. This is a matrix corresponding to E. So our result is verified. C2 into C2 is V. Let us take C2 into sigma xz. Our table for C2V point group shows result should be CYZ. Now I take the matrix corresponding to C2 and matrix corresponding to sigma xz and multiply it. I get a matrix minus 1, 0, 0, 0, 1, 0, 0, 0, 1. This is nothing but matrix corresponding to sigma yz. So this is also verified. Now let us take C2 into sigma yz and the result is sigma xz. So I take the matrix corresponding to C2 corresponding to sigma yz and multiply them together. I get 1, 0, 0, 0 minus 1, 0, 0, 0, 1, which is nothing but matrix corresponding to sigma xz. Let us take the another product sigma xz into sigma yz. Here again I take the matrices corresponding to sigma xz and sigma yz and multiply them together. The net result is minus 1, 0, 0, 0 minus 1, 0, 0, 0, 1. This is nothing but matrix corresponding to C2. Thus all these four matrices which I have obtained, they form a representation for the C2V point group. And you can verify all other products also. You take C2 inverse, you take sigma inverse, any of this operation you will take, they behave very, very similar to operations of the C2V point group.
Let us now try to examine some of the symmetry operation products and that of corresponding matrices. So first of all, let us consider the C2 into C2, which will be giving us E, that is the E operation. So first of all, let us consider the C2 into C2 and try to understand that on applying C2 operation 2 times, we will get the E configuration, that is doing nothing. So if we take this C2, which we already know is represented by this matrix, it is minus 1, 0, 0 and 0, minus 1, 0 and 0, 0 and 1. So let us take this C2, and to differentiate, let me take this C2 with this color red. So we have again this is same minus 1, 0, 0, 0, minus 1, 0 and 0, 0, 1. So both 3 by 3 matrices. And now if you look at the product, which we'll get is, you'll have this minus 1 and minus 1. So this is going to give you 1. 0 into 0 is giving you 0. And from here again we get 0. 0 into 0 is again 0. Minus 1 into minus 1 you get 1. 0 into 0 you get 0. 0 into this 0 is 0 again. Here also we get 0, and 1 into 1 is 1. So what you have got is this, which is nothing but E. The next case we take is, let us try to apply the C2 operation followed by sigma xz operation. So we'll multiply the C2 with sigma xz, and we will see that these two operations, that is C2 followed by sigma xz, will give you configuration which will be equivalent to sigma yz. Now in terms of matrices, let us see. So C2 we know is represented by this matrix, and sigma xz will be this matrix. And now when we multiply them, what we get is minus 1 into 1 will be minus 1, 0 into 0 will be 0, 0 into 0 is 0 again here. This gives us 0. Minus 1 into minus 1 is 1. 0 into 0 is 0. Here again we get 0. Similarly here, and 1 into 1 is 1. And what you can see here is this is nothing but the sigma yz operation. So what we can say is, on applying C2 operation followed by sigma xz operation, we get configuration which is equivalent to sigma yz. The next case, let us take that C2 operation is followed by sigma yz, and we will see that this combination will be equivalent to sigma xz. So C2 is this matrix, and sigma yz is this one, and the resulting, that is after having these two operations, it will be the product of these two matrices. And let us see what we get is minus 1 multiplied by minus 1, you get 1. 0 into 0, we get 0 here. Again 0. Here also 0 into 0, we get 0. Minus 1 into 1 will be minus 1. 0 into 0, then again 0, and then again 0, and 1 into 1 will be 1. And this is sigma xz operation. So first applying C2 and then sigma yz operation, what we get is equivalent to sigma xz operation. Let us see now what happens when sigma xz operation is followed by sigma yz operation, and we will see that this will be equivalent to the C2 operation. So let us write these two corresponding matrices. We have sigma xz, which is equivalent to this matrix, sigma yz will be this one, and now what we get is 1 into minus 1 is minus 1, 0 here, again you get 0 here, this gives 0, minus 1 into 1 is minus 1, 0 into 0 is 0, again at this place we get 0 and 0, and 1 into 1 is 1. And this, you are familiar that this is nothing but the C2 operation. So what we can say is, when sigma xz operation is followed by sigma yz operation, it is equivalent to C2 operation.
Now, in this module, we have learned more about representation. It has been explained by taking various general point groups used for generating representation of symmetry operation. Representation generated using rotational vectors has also been explained. Position vectors also were used to generate the various representation for various symmetry operation of C2V point group. And after generating these matrices, the symmetry products or symmetry operations have been verified. What are the various symmetry operations and their products? What are the products of the matrices corresponding to these symmetry operations? These have been found and the results are true. So it gives that a 3:3 matrix representation using general point group or any other basis, we are getting matrices which behave very similar to the symmetry operations of the C2V point group. Hence, the symmetry properties have been quantified in terms of numbers for the representations.